I'll just start whenever the screen pops up. And I mute myself because. Okay. All right. We are live. Hello, everyone, and welcome back to our Introduction to Python course. This is a recap of Unit 3, input and I told Dr. Sakk that I would say input and output because I can't not say them together. But that is not the name of this. Is input and flow control statements as part of Sailor Academy's CS 105. This is again the recap of Unit 2. If you haven't started the course, you can go to sailor.org and find the course. You can also, if you haven't caught up to Unit 3, we've done recaps of Unit 1 and Unit 2, which you can find on this YouTube channel. All of the links should be in the description below. If not, I'm going to put them in the chat right now once I hand it over. And of course, feel free, if you guys want to have a conversation outside of this chat or outside of the comments, you can go to the discourse forums at discourse.sailor.org. And I think that's everything. And if I forgot it, I'll bring something up later. But right now, I'll hand it off to Dr. Eric Sakk to take it away.
Fantastic. Thanks so much. Thank you. Nice to see everybody this week. And just want to quickly, briefly talk about the input statement. I will probably give it about 1 minute or so, just because it's important to understand, as it says here in the course itself, that when you are expecting input, the input instruction is going to return a variable of type str, and that's surprising to some people who first start out, because sometimes you want a string, sometimes you want characters, sometimes you want to type in somebody's name, or the course they're taking or something like that, and that will require text. But oftentimes when you're getting input data from the keyboard, you want numbers. You want to calculate something. So when you want to calculate something, you have to take the intentional step of converting the string to either an integer or a variable of type float. And so there are examples in the course down around the second paragraph that kind of tell you or teach you or show you what it takes to convert to an integer or convert to a float. It's not hard. You just drop the input statement into a float instruction with 2 parentheses around it, and that's the syntax for doing that. And then you would convert it to a floating point value. But just if you have any questions about that, you can raise it. Otherwise, I think it's very straightforward to do. But sometimes when people are first starting out, they have to be reminded. They have to be reminded of how to make that conversion, because it's an intentional conversion. Again, with regard to data types, when one is first starting out, learning a computing language, and you have to start, kind of fielding all these different types of data invocations, data type invocations, it can get a little confusing, but it's just because the computer represents data in different ways. You're helping the computer out quite a bit when you're invoking a certain data type. So anyway, that's there. What I think that the time is probably most usefully spent today is where it could be spent is on conditional statements and on loops. And whenever I teach, and this is also in the course as well, whenever I start to teach about conditional statements, I try and show flowcharts, and flowcharts again are, sort of like at the introductory level, sort of a pictorial representation of what your computer program is supposed to be doing. And even these days, people don't use them that much. But if you start to do this for a living, you find yourself scribbling stuff on the back of an envelope when you're thinking out an algorithm, trying to solve a problem. And, you start scribbling down these little pictures of what the flow of the computer program is supposed to be doing. They can be, quite useful. Now, I'm not even an expert flowchart maker. I mean, if you go into the ANSI standard and you get, the real flowchart people, they're very very territorial about the pictures that they make, and the various diagrams and what they, the tools that they use to build diagrams and so forth. I'm just not of that camp of people. All I want you to understand is how to sort of draw. Some people are left brain, some people are right brain, some people are more analytical, some people are more artistic and picture represented. And it's good to have both sides. It's good to have this coding side, and it's good to have the picture side to be able to, arrive at a solution to, if you're writing a program, arrive at a solution to a problem. So, and that's the way it is. So really, when I write flowcharts, there's really only three tools that I use. I use a diamond, I use a box, and I use a circle. And the circles are for start and stop, if I wanted to actually make it clear that the program was starting someplace or stopping somewhere else in the control flow. But then the diamonds and the boxes are important to me because the boxes represent stuff that needs to be computed. Oops, like this. Here we go. So here's a flowchart. So the boxes represent something that needs to be computed, and the diamonds represent decisions, and the decisions are what make a computer a computer. If you really ever get into the theory of computation, if you really ever dig deep enough, what you'll find is that unless you have those little diamonds in your program, all you have is a calculator. All we've done to this point, with operators and relational operator, I've taught you how to build a calculator. Basically, I've taught you the syntax to do what you could do by pressing a button, a bunch of buttons on a machine. But we want to do more than that. What we want is an automatic computing machine, an ACM, something, or what some people refer to as a Turing machine. A Turing machine is something, if anything in the universe is computable, a Turing machine can compute it. And one of the fundamental components of a Turing machine is the ability to make decisions. And once you have a system that can make decisions between one potentiality and another potentiality, then you have a computer. You really have a true computing machine at that point. Before that, you don't. And so the diamond that you see here is very, very important to developing or designing a computer language. All computer languages, if they claim to be a computer language, have some form of if statement, give you some capacity to compute conditions and make decisions based upon those conditions. And in Python, there are if statements, and there are also if-else statements, and there are if-else, else-if, or elif statements. You can create a whole stream of conditions that you can sort of implement within a computer program. So this little diamond is incredibly important because it's like your program to the right. You can see it's whatever's running sequentially, instruction, dot, and then you bump into this if statement. And then the if statement, and again, at the introductory level, this sometimes blows people's minds away. It's very simple, but it's very important, is that the if statement is going to decide between one potentiality and another potentiality, and it's not going to execute both of those potentialities. One is going to be left alone. One will not be executed. It is conceivable that you could write a program where certain sections of your program, where there are lines of code, may never be executed. They may be sitting in your program, and because of some condition, the computer jumps over those, branches over those instructions, and does something different based upon a decision that was made. And it's very important to understand. Some students, like I said, when they first start out, they're like, wait, I got these instructions here, but they're not going to be executed. It's like, whoa, wait a second. Yeah, well, it's true. And so in this case, that's what the diamond, that's what the picture is telling you, is if some condition turns out to be false, then you're going to continue program execution. Program control is going to bypass this other group of Python commands. They will not be executed. However, if the condition is true in this case, then they will be executed. Again, this flow chart is in your is in the course. It should be there. And then, of course, maybe it turns out that you want to not just jump over a bunch of instructions, but you want to execute two sets of instructions. If this is true, do this. Otherwise, do something else. Well, in the otherwise case, you've got a whole section of code. That's the indented Python commands group 2 now. And whenever the syntax, hopefully you understand at this point, if not, we'll go over this in a second, but I'm just giving an overview, is that when you have the if condition, the syntax is to end whatever that condition is with a colon, and then you indent everything that you want to do if the condition is true. Otherwise, if the condition is false, you have another set of indented instructions. And it may just be one. It may be one instruction, and there's a utility. The else part of the if is going to execute those other instructions. So once again, you've got two sets of instructions, only one of which is going to be executed. The other won't. I mean, you've got a binary decision, and in general, binary means true or false. You're going to do one thing or the other thing. You're not going to do both of them. So there could be code sitting here again that may not be executed. And then, of course, when you start to write more complex programs, well, then, you could have a whole sequence of conditions that you need to, like if you build a menu, right? You're going to build a menu and someone's going to enter a number, you have like 10 choices, and each of those choices has to be available to the user. They're only going to pick one, but there could be 10 sitting in your code. So you write a menu, if 1, do this, if 2, do that, if 3, do that, if the user enters 10, do this. So this is what the if-elifs are for, is because it enables you to write a long sequence of if statements. If it's true, do this, else do this, else do that, else do this. Now, excuse me, other languages, and this is why I like Python so much, because it's so minimal. Python seems to have looked at other language and just thought, why are you doing this? There's just so much there. There's too much there. I'm a minimalist, and so there are things about Python that are very minimal. In other computer languages, you'll see something like, for example, a switch statement. And a switch statement basically is like an if-else kind of a statement, except it assumes that you've got some condition like a number, and then it allows you to numerically outline each one of those conditions. Python has no switch statement. So if you programmed in other languages, I don't want to burst your bubble. I know some people love the switch statement. I'm not a fan of the switch statement. I'm a minimalist because I know underneath the hood, there are just a bunch of if-elses. So why not just write the if-elses? That's kind of how I think. But other people like the elegance and the simplicity of switches. So if you're coming from that background, just kind of little full disclosure, Anyway, let's pop over to the replit window, and oops, I didn't mean to do that. And so, we'll set A equal to 234, not a very exciting number, but if A is equal, and this is where the relational statements come in, by the way, when you're testing if statements, you have binary condition. So if you have basically it's a Boolean condition, but you're writing if conditions with the intent, either intentionally or not intentionally. I mean, again, some people take a little while to get this, but whatever gets evaluated in the if condition is going to be a Boolean statement, and it's going to be evaluated to either true or false. So you could even have mathematical statements. You could have arithmetic statements in your if statement. But at the end of the day, the way the if works is it's going to evaluate a Boolean statement. So here's an example of an if else. I just want to make sure we've all got the syntax down. So very straightforward. You've got the colon. Remember, and I just want to say this. I always. This is a cautionary note, in terms of what it means to program. The 50% is learning the syntax. You've got to get the syntax right. Because as I said before, every computer language, has some form of a conditional test of some kind. And oftentimes it's like an if statement of some kind. And so it's important to learn the syntax for each language. It's a little bit different, there are differences. And if you start to program, if you program in like 5 different languages, you start to mix them all together, which is always fun. But I'm just saying, so for Python, you got to have the condition, and then you got to end that statement with a colon, and that's Python syntax to say, hey, I know, just like we've done, and we will be doing. This is very normal. This is going to be very consistent, and you might as well just emotionally prepare yourself for the fact that this colon is going to pop up all the time now, okay, for the rest of the course, because that's how Python understands things, not just if statements, but there'll be a whole host of other, utilities and tools that we learn that are going to require that colon. And then after that, anything that's indented is considered to be part of the if clause, and that's what's going to get executed. So that's how it works. And then if I change A to 235, then of course we're going to execute the other potentiality. So again, it's not difficult. It's a very simple concept. But like I said, when students first start out, it's a little strange to them that they're going to have commands in their program that could potentially not be executed. And that's just the way it is. It's how computers work. The ability of a computer to make decisions is fundamental to computation. And again, you don't have a computer without them. And so coming back over here, really, this is the most important concept is when you start to write a series of if else's, that there's an ordering. Okay, pay close attention to this. There's an ordering to the decision-making process. Okay, and the decision-making process is, it kind of goes where the if is checked first, and then the next LF, and then sequentially the next LF, and then sequentially the next LF. Okay, what do I mean by that? Well, if we do something like this, let's say LF, and I have another condition here, maybe if A is equal to 234, and we'll make A equal to 234. No, I don't know why you might want to do this, but I'm just trying to point out that the decision-making process takes place sequentially, and then only one of those potentialities is going to be executed. LF, A equal to whatever. Then do this. Oopsie daisy. LF, that's great. There we go. I don't need that. And so, obviously, the way that I've set things up so far is that A isn't equal, and then maybe I'll throw an else in here as well for the heck of it. Oops. Something like this. So here, just to kind of give a tangible, not doing anything really exciting. This is not the most exciting program in the world, but if I, oopsie, and I gotta indent that guy. All right, so I've got all these indentations now, and within each indentation, that defines the branch of the if statement or the elif statement that will be executed under the circumstance where the condition is true. Okay. And notice I've got two conditions that are exactly the same here. Okay, and if this condition is true, we do this. If this condition is true, we do that. And again, you got to go back to this picture to make sure you understand that this is a sequential process. And when the decision is made, you're done. Okay, it's bye-bye. You don't even pay attention to the rest of those if-elifs. Okay, you're gone. You're on to the next thing. And that's what this is sort of the left brain picture, and then the right brain side of this is all the code over here. So once you execute a potentiality, then you're down, then you branch or you jump, depending on what's happening underneath the hood and what the syntax is. You think of branching or jumping, you jump to another place in your code, and effectively you disregard all this other stuff. I mean, that's why you're writing the if in the first place. So just want to make sure we get that, So if we were to analyze what happens here in the extreme case where I test two conditions simultaneously, then, we want to see what happens. Obviously, the first condition is printed out, and then the second one is disregarded. We never pay attention to it. So even though A is true, because of the fact that we executed the first if, we jump, all the way down here, and we might say, bye or something like this, and so we jump down to the end of the if statement. If I can get this thing, if I can type right this morning. So all those other potentialities, in some sense, are disregarding because you satisfied the first one sequentially. And it could be that another condition is actually true. Now that's bad code as far as I'm concerned, but I'm just trying to highlight the point that, you got an if statement with like a whole bunch of conditions that are the same. That just doesn't, there aren't many places where one might want to do that. But I'm trying to highlight the fact, highlight this picture where once that chunk of code is executed, you go into that particular branch of the if statement, and then you're done, and then you sequentially go on to the rest of your program. So that's program control. That's called program control, because you're controlling, at the low level, really, you're causing the central processing unit to start. You're jumping around. You're causing the CPUs to think, oh, I've got to go here, and then I've got to go there, and then I've got to jump over here. And when you start doing that, that's when you're really computing. That's when you're actually doing something interesting. So hopefully everyone gets that. That's sort of the first part. Well, there's the input, and then there's the first part of Unit 3. And I'm happy to stop for any questions with, if, elifs, if anyone has anything. So there's syntactical issues, and then there's implementation issues, understanding how it works. And then as you start to use these, this is where you start to learn to program. We're not really programming in some sense, because we're not solving any problems. We're not writing any algorithms, but you got to know the syntax for implementing this type of a structure. This is probably one of the most important structure. I can't overemphasize it. It's like you don't have a computer without this. So happy to take questions at this time, if there are any.
Well, I'll tell you right now, I think the first thing everyone should do when the stream is over is look up what a Turing machine looks like, because it's basically looks like a cassette tape or a videotape, but the size of a table, and it's pretty crazy looking. But yeah, the question that I think was posed maybe a couple weeks ago, but since I don't remember the answer, and I'll wait for the chat to catch up. The double equals sign on the if statements.
Yeah, so great question. And this is really this is why Unit 3 comes after Unit 2. Is in Unit 2 we learned about operators, and they were arithmetic operators, and then there were and in Unit 1 we learned about the assignment statement, by the way, also. So Unit 1 talks about the assignment statement for the equal sign, which again is kind of like you're thinking of taking whatever's on the right side of the equal sign and then plopping it into whatever's on the left side of the equal sign. I guess you're looking this way. And then we learned about operators after that, and we talked about relational and logical operators, which are only allowed to give answers that are Boolean, that are binary in their nature, which are true or false. And so this is, again, one of the, and I think even when I know I've done it, professional programmers even do this as well sometimes when they're not thinking, they're just sort of doing stuff automatically, like an automaton. And so here's the assignment statement. Here, the equal sign is being used to assign the variable a the number 234. So whatever's on the right side is being transferred into that variable on the left side. So we know after that instruction executes that the variable a contains the number 234. Okay, until it gets changed later on, until we do something else with it. But that's what it's currently been assigned the value of 234. Now, when we come down to the if statement, we talked about relational operators. And just to review Unit 2, the relational operators were greater than or equal to, less than or equal to, and the double equal sign means equality. So it doesn't mean you're assigning a value. It means you're testing something. You're saying, A equals B. And when you do something like this, the only possible answers, just like for all the relational operators, is either true or false. If A equals B, you get a Boolean true. And in Python, that's actually the word true. That's a reserved word. And then if A does not equal B, you get a Boolean false. And that's really what the goal of the if statement is. You're trying to figure out basically whether or not a condition is true or false. Because the if is only capable of evaluating Boolean expressions. It's only going to execute based upon whether something is true or false. That's it. That's all it looks for. It doesn't look for numerical values, although you could drop numerical values into an if statement, but you got to know what you're doing. You got to really, because all languages are a little bit different when it comes to making decisions on numerical values other than Boolean values. So right now we'll just keep it in the Boolean space. And so this condition is only going to evaluate to either true or false. If A is equal to 234, well, then we're going to do this. And A is not being assigned the value. This is a test. And all it is a test. You're not assigning anything. So the value down here is of A is in fact it's still going to be A. Nothing changed. Nothing got reassigned. The double equal sign is just a Boolean test. Okay. And that's all there is to that, because relational operators, the reason that we introduced them in Unit 2 is because we're planning on using them both for if statements and the next subject we're going to get to, which are going to be loops. So if statements can only make binary decisions, and those binary decisions usually, 94.3% of the time are based upon the outcome of a mixture of relational and logical statements. So we could do something like this. We could say, B is equal to 4, 5, 6, 7. And then we could do this. We could mix, and we could say, and, B less than 1,000, let's say, okay? So if you have now this condition, we talked last week, this is why it's so important to understand those relational and logical operators, is if A is actually equal to 234 and B happens to be less than 1,000, then we're going to, so we don't execute that condition. Why? Because B clearly is not less than 1,000, but if we make it less than, let's say 10,000, then that would be true. And so now we go ahead and execute this instruction. So the whole point of introducing logical and relational operators is that, so when you're comfortable with them, now we can start to apply them with if, else, and elif statements, because we're actually testing those logical conditions. So it has nothing to do with assignment. It has nothing to do with the equal sign. It has nothing to do with the assignment operator. And that's kind of the flow of the course. Unit 1, we talked about the assignment operator, because you've got to learn how to assign variables. Well, what kind of variables? Well, the kind of variables that are either string, float, or integer so far. And so that's what we start with. So you learned you learned about data types and the assignment statement. Then we go into Unit 2, where we say, okay, well, now you know how to assign variables. What do we do with them? Well, one thing you do with them is operate on them with arithmetic. You can add, subtract, multiply, divide, take power as integer division, those sorts of things. And then the next thing that you want to know, we wanted to prepare you for, was this unit where relational and logical operators, the major place where they're used is in if, else, and elif statements, because you're trying to ascertain some logical state based upon the condition of a set of variables. The double equals is infinitely different than the assignment statement, because it is intended to evaluate to a Boolean true or a Boolean false. Hope that answers the question.
I'm sure that over answers the question. So we did get one question. We got a question while you're doing that, and it's about the else versus elif statement meanings. Like,
well, again, the best thing to do is to have this picture in your head, because the elif is just it means you're not done testing conditions. It means you've got like a host of conditions that you want to test. And so elif is shorthand for else if. Most languages have else if. That's usually, and again, Python, for whatever reasons, that probably happened so long ago. But the condition else if it's like a contraction for elif. So it's just your program could potentially have a number of conditions that you're trying to test. So it could be like if, else, if this is true, do this, 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 And so this series of commands, you can put as many elifs as you want, and you can create a series of conditions, a series of test conditions, and test each one of them, and the elif would be used to do that. And once again, the picture or the code structures that you would use is that if something is true, then execute this group of instructions. Else, if this is true, then execute this. And then the else is kind of like, and you don't always need one, but it's like cleanup. If it turns out that you kind of left out any conditions that weren't contained, and you're writing code that depends on you addressing anything outside of the set of conditions you've already addressed, then everything gets sort of plopped into the else condition, basically, So, if you, and so the picture, once again, is if only one of those potentialities is going to execute. So, you could have if A is equal to 234, else if, A is greater than 234, do this, and else if, the A is less than 234 or 345, and A is greater than 1 or something like this, and then else everything else. So if we happen to make A -1 or something like this, then you wouldn't execute this because it's not equal to 234. It's not greater than 2. It's not less than 345 and greater than 1. So I don't need to state a condition. I'm just trying to clean up things so that if I left anything out, that's one way. You can think about it. I wouldn't program that way. You want to have a flow chart that kind of defines. It depends. If you're doing it for fun, no. But if you're designing a grid for a telephone system, you probably want to have that else in there just in case. So. And people haven't, and so whole power systems have gone down because of that, unfortunately. So, the else is kind of like the cleanup for any conditions that you may have left out by defining them with Boolean expressions. I hope that answers the question.
Well, I don't want to give you a big head or any hubris or anything, but I can confirm that the person that asked this question says that. Thank you, and they now understand the difference. So you did a good job explaining, I think.
All right. Okay, so let's move on now. If there are no questions about conditionals, because again, it's something that you want to get really, really good at. It's something that I have found personally, just from teaching this stuff, for at least for the last few days, that sometimes students come through the conditional unit on the other side of it, not fully embracing it. And so I really, like I said, I do everything I can to reach the left brain people and the right brain people with either a picture of the code so that everybody is like 1,000,000% clear with it. It's not difficult, but if you don't know it, you really can't program. You're not able to logically define sets of conditions with these combinations of relational and logical operators. And that would be a shame. Like I want everybody. It's such an important tool, and I just want you to know it inside and out. That's all. All right, on to loops, and we're gonna play a game, and the game is I want to count. I'll start counting at 0, let's say, and I'll add. And I'm going to count by ones, and I'll do this again and. Keep on doing that. I'm going to keep on adding 1 to my I. So I'm just adding 1 to I and 1 to I. And let's make believe that I'll stop here just for the heck of it. And I got a little syntax error here, so we got to fix that. And let's make believe that I want to. I'll print the value here. Print I. So like something like, oops, made a mistake there. So that's replit. Okay, I blame replit. Sometimes see these editors, they'll make decisions for you. And I don't want to do that. Okay, well, it did it anyway. There you go. All right, so far I've counted to 6, but let's make believe that I wanted to write a program that counts to, for instance, 100 million. And I don't think we have time for that. So maybe by next week when we come back, I'll be done with this program, because it's going to take a while to do that. And so on and on and on. When it comes to the concept of loops, and that's what Unit 3 is also about. Again, just going back to a Turing machine, and And the concept of doing something over and over again, and the program construct, the syntax for writing what's called a loop. You're planning on writing a program, and you know you're going to do something over and over and over again, similar operations, and make believe you wanted it, and it wouldn't be unthinkable. Actually, it's normal to have to do something, 100 million times or a billion times, using computation. And what do? Well, you could write out 100 million statements or a billion statements, but those programs would get very long. And so for the theory of, if you want to be really theoretical about it and really press the issue to a purist theoretical computer scientist, it could be argued that you don't need syntax that would make it more compact to write something called a loop, which is something you do over and over again. But I'll tell you something, it sure is convenient. So, and that's really where loops come from, is the convenience and the importance of making compact programs. So when we talk about loops, we talk about things like a for loop, for instance, and a for loop is basically something that try to make decisions for me here again. I love Python, and then you can hate it as well. So it's but when you're going to count, okay, so the for loop is basically something that gives you the ability to count. And if you want to count, because you're planning on do something 100 million times, you kind of have to define three things, either implicitly or explicitly. You've got to tell where to begin counting, where to stop counting, and what your increment or your step is going to be. Because I could have just as easily, if I walked up to you on the street and said start counting, and you started counting at the number 5 and started counting by twos, you would have satisfied my command to start counting. I didn't tell you where to start, and I didn't tell you where the increment was, and I didn't tell you where to stop. But for loops need those, either implicitly or explicitly, need those three pieces of information. Basically, for loops count. That's all they do. So I could say something like this. I could say for, and you've seen this in the course as well. I could say something like for I in range, 5 or something like that. And what the range, it's a function, and we'll get into functions within the next couple of units. I think it's unit 5, but I'm going to tell you ahead of time right now, that a function is something that you drop data into and you get an answer from. And we're going to start writing these ourselves, user-defined functions. But there are functions that you can call and that are built into Python. One of them is this range function. You drop a number in, and what it will do, actually, it'll create something called an iterator. And an iterator, when you iterate something, it means you're going to planning on doing it over and over and over again. That's what it means to iterate. To iterate means or iterate, depending on what part of the globe you're from. I got a funny story, but I'm going to leave it out, though. I'm not going to go there. Anyway, so well, maybe another day. And so, but when you're iterating, you're planning on doing something over and over and over again. And so the range function, you drop a number in, and it'll give you an iterator that you can drop into a for loop. And the for loop, when you drop this 5 in, really, honest to goodness, knows that you are planning on iterating on that variable. And notice, I'm dropping the number of 5 in. I'm not telling it where to start, and I'm not telling it where the increment is. Well, the range assumes when you give it a variable, and we'll get to all that in a second. But right now, for the introductory phase, when you tell it range 5, it's basically going to count increments by 1, starting at 0 to 1 less. It's going to do 5 things, but it's going to start at 0. So it's going to go 0, 1, 2, 3, 4, because that's 5 things. Okay. And notice I haven't told it where to start. I haven't told it what the increment is. So the range, if you don't give it that information, it's going to assume that's what you want to do. And this variable I, every time you go through this loop, it's planning on doing this loop 5 times. Notice there's a colon again, just like the if statement, and you've got an indentation. So anything inside the indentation is what's going to be done over and over and over again. That the variable I is a bona fide variable. It's a true variable, and it's going to change every time I go through this loop. And you can use it as such. You can, it really is something that's being reassigned every time you go through. It starts out at 0, it's going to go to 1, it's going to change to 2, it's going to get reassigned those values. So it's not, when it loops, it's not going to remember as it's counting. When it gets to 3, it's not going to remember the number 0 anymore. And so every time you go through the loop, each time you do it, this is basically doing what I was trying to do before, which is I plus equals 1. That's really what's happening. It's counting from 0 to 4. It's going by increments. Now, I could tell it where to start. I could say something like, start counting at 3 and count until 10. And now I'm giving it the syntax for starting to count at 3 and going to 9. And this is one thing you're going to have to get used to if you're not used to it already. It's just when you start to think in terms of certain computer languages, one of the things that you do, some languages start counting at 1, some languages start counting at 0, and then when you give it an endpoint, some will go to the endpoint, and then others will go to like 1 before the endpoint. So it's really, the condition is not count to 10, but it should be something like count while I is less than 10. That's a good way to think about it. That's actually how it's encoded, from a low-level standpoint. So the idea is that you go, just whatever you're counting, you go 1 before that value of 10. So 10 won't be included on. If you want 10, then you have to remember that you have to go to 11. Okay, right? It goes to 11. I don't know if that's this is from the ancients. It goes to 11. Anyway,
I got it.
You got it. So anyway, and that's counting. That's basically it. But you can do more than loops than just count. I mean, I just want to make you aware that when you're planning on doing a for loop, you're basically planning on doing something over and over and over again. And anything inside the anything inside. I was gonna say anything inside the brackets, but that's the wrong language. See what happens here? I'm losing my mind. Anything that gets indented, okay, is going to be executed within that loop. So that's all there is to it. Now, so there's the starting point, there's the stopping point, and if you want, you can create increments as well. You can say, well, count by 2s now. Don't count by. So now I'll go 3, 5, 7, 9. It's not going to go to 11 now because 11 would be the next number in the sequence, but we're not going to 11. We're going to whatever's 1 before in terms of the count. So really, when you use the range function, in disguise, you've got to give it the starting point, the end point, and the step size. Okay, and by the way, and you should remember that. You should remember that because that's going to be the ordering of the syntax for many things that we do for the rest of this class. It's going to be the start, the stop, and then the step. That's the order. Some languages aren't like that. Some want you to give the start and then the step and then the stop. So again, depending on what background you're coming from. In this language, it's start, stop, and then step. And if you leave any of them out, then Python is going to make assumptions for you, because the goal of Python is to always keep running. And so you shouldn't have to crash because you left something out. It's just going to do something for you, and so you need to know what those assumptions are. So that's how a for loop works. It's just, and you can use this value any way that you want to. You could say I star squared. Tell me I squared. And so now when let's say we count to 5 and we want to know all the squares between. Okay, or you can have a number. I could set x equal to, so watch this in slow motion now. So I'll set x equal to 1, and then what I'll do, and I'll set x equal to 1, and then what we'll do, I'll print out, I'm printing these. You don't have to print them in loops, and oftentimes you don't want to. I'm just trying to give you an immediate feedback as to what the loop is doing. And so what I could do is I could set x equal to, let's say, x times I, for instance, something like this. And I'm sorry about that. Maybe I'll set x times x. That's what I'll do. And so what I'm doing here is I will be, let's say, multiplying. Let's do it like this. I'm actually going to play with this a little bit later today too. So let's do something like this. Now I'll set x equal to 1, in fact. 1, everybody. There we go. And I'm at 1013. So in this case, what I'm going to do is I'm going to print out powers of x. I'm raising x, to the ith power, basically, because I'm successively multiplying x by the number n. In this case, x starts out at 1. The first time you go through the loop, 5 times 1 is 5. So X gets reassigned. And again, this is the big deal about loops, is that when you start to reassign variables, again, you know, as soon as you kind of know what you're doing, the intent, maybe the intent is for me to raise, you know, 5 to the 5th power, let's say, if I wanted to do that. Again, you can do that with one instruction. So that's not the goal of this example. The goal of this example is to show you, you know, how a loop could be used to successively compute something. In this case, we're taking n and multiplying it by itself, you know, over and over and over again. So the second time is 5 squared. The third time is 5 cubed, 5 to the 4th, 5 to the 5th power. So this is how you start to use loops, is you make computations and then you reassign variables, and then with for loops, there's like a predefined counting process where you know how many times you want to do something, and you know where you want to start, and you know what the step is. So that's all I want to say about for loops, just to kind of, you know, kind of point people in the right direction for this unit, to make sure you understand what the point of loops are. They're very important. They're indispensable, because if you didn't have them, like I said, computer programs would get unacceptably, impractically long. You know, they'd be too lengthy, basically. Any questions?
Great. So, so I'll give everyone a chance to catch up. What I will say is, I got the Spinal Tap reference. I was worried because the first thing you were talking about conjunctions, and the first thing that came to my mind was Schoolhouse Rock, which is considerably older than Spinal Tap. But don't worry, I did my research. Schoolhouse Rock started in 1973. Mm-hmm. Spinal Tap came out in 1984. But I still have a younger reference because the episode Grammar that featured conjunction junction wasn't until 1996. So,
oh my God. You were so helpful. I mean, it's like these facts here. This is great.
Oh, right. It seems like everyone's good, so I think we're good to go on. If I have anything else, I'll raise a hand for it.
Okay. Great. So the last thing I want to talk about are while loops. And again, when you go to different languages, you know, they give you more constructs for writing loops. You know, some languages have do while or do until. And, you know, Python is very minimal in the sense that it just gives you for loops, because it's boiled down all computing languages to the concept of either counting or doing something based upon a logical condition. And when you want to write loops that are based upon logical conditions being satisfied, that, you know, a for loop wouldn't be possible. So the while loop, you know, maybe we'll have a variable like, you know, again, the letter A for nothing better for the, and maybe I'll write a while loop with a condition that says while, you know, A is less than 5,000, let's say. Again, this will get not the most exciting loop in the world, but a loop nonetheless. And then what we'll do is we'll say A plus equals, let's get through this quickly, 400 or something like that. We'll add 400 to it. So here what's happening is we're testing a condition using relational operators. So while A is less than 5,000, we're going to do everything inside the loop. And that says print A. So it prints A, and then it adds 400 to A. So it becomes 4967, and then 4967, and then it'll print 4967. It'll add 400 to A, and then it'll come back and test that condition again. So every time you loop back to the while statement, you jump back up here, you test this condition, and you ain't leaving the loop until the condition is satisfied. And that could be a great thing, or, you know, for people who are starting out, that could be a really dangerous thing, because you could end up, like, if I never increment, if I accidentally never increment A, then we could just, this goes on forever. That's called an infinite loop. And those are generally frowned upon in the computer science world, because your program isn't stopping. And it's some famous, again, theorems about knowing, can we ever know whether or not a program will actually halt, will ever stop? It's called the halting problem. And it's a deep problem because so many other problems in computer science can be mapped onto that problem. By itself, really the question is, can you look at a program and know whether or not it's going to stop in general? If I showed you any program, and obviously this one is fairly straightforward, but I'm just saying, in general, it's not possible to do that. So that's called the halting problem. And then, that it's a deep concept because the complexity of problems in computer science sometimes can be transformed or mapped onto that halting problem. And then you can decide whether or not your program, could have a provable solution. And sometimes that's not always the case, sadly. And sometimes it is. And when it is provable, then that's great. Then everybody's happy and everybody goes and starts sipping pina coladas on a beach somewhere because you solved the problem. But sometimes it's not true. So in this case, the program doesn't end. And that's the way it is. So you don't want to write, starting out, your goal is not to write programs with infinite loops. That's considered, like I said, not to be such a great thing. Anyway, so that's the while loop. And the while loop, again, the intent of the while loop is to give programs the ability to iterate based upon logical conditions. Now, you can turn a while loop into a for loop. You could set I equal to 0, and then I could say, I plus equals 1 will increment by 1, and while I is less than 10, and something like this. So usually it's possible. It should be possible. I mean, theoretically possible to turn a and then I'll put this up here, sorry. Bam. So notice where I put the print statement is very important. If I print it out after or before I increment, that's a big deal. I know that seems like it shouldn't be a big deal, but again, there are languages that go back and test conditions either before the loop is executed or after the loop is executed. It is, in some languages, this is a big deal. I'm not going to make a big deal out of here because you've only got the while loop, but I am alerting you, if you learn other programming languages, it is important where you put that print statement in the context of like a while versus a do while or a do until and all these other constructs that people give you. But if you're just using the while loop, notice that if I put the print afterwards, I'm going to print the value out. And the idea is that the I value goes back and gets tested against the 10. So I just turned this while loop into a for loop, okay? Because this is exactly what I did with the for loop before. It's not always the case that you can turn a while loop back into a for loop, because if you really have real logical conditions, it's a lot easier to express those logical conditions in a while loop. So if you're thinking about something, probably the place where this could be useful, and I think I do this in the course, is like you're waiting for input from the user, and then the user does something that you don't want the user to do. And so then what you do maybe is you set flags or something like this. This is a very, very common use of while loops. You set a flag and you set it equal to false or something like that. So I set in flag. I'm going to call it input flag. I'm running out of time. I'll do this in about 2 seconds. So stick with me. So while in flag, okay, something like this. Notice I'm not really saying anything important with in flag. In flag is a Boolean variable. It's of type bool. Okay, so I know it's a Boolean condition, and the while loop is kind of like the if statement. It's testing Boolean conditions. It wants to know if a condition is true or false. I apologize. I'm going to make this true, or otherwise we're never going to get anywhere. And then what you'll do is, while in flag is true, you might say, z is equal to input something where you say type a number, between type a number between 5 and 10, or some type a number between let's say 5 and 10, something like this. I'm just kind of doing this. And so when you do that, if let's say z is less than or equal to 10, and z is greater than or equal to 5, then set in flag equal, for instance, to false. Okay. And then maybe what you'll do is you'll say else, otherwise, print something like, bad input, you see. And so this is a common use of, and then maybe I'll print, done or something like this. So this kind of a loop, basically it uses in flag to set a condition, and then you're not leaving this loop until you get the input that you want. Okay, so while in flag is true, you stay here, and you wait and you force the user basically to kind of do what you ask them to do, because that's the way you write software. You never write software assuming the user's going to do the right thing. That's why you have beta versions and alpha versions, because you send it into the public domain to let people try it out and do all the stupid things that anybody could ever do that you never thought of as a programmer, and then you fix them with these kinds of if statements and while loops and so forth. So you could run something like this, and maybe I'll type in a number, like 34. It's like, hey, I told you to enter. You see, so what I got here? So I've got some kind of what did I do here? I did the thing, right, that said, hey, don't do this. You got to turn it into an integer, right? So let's turn it into the number 3 like that, and bad input. And then I'm just, I'll sit here until, there used to be an AT&T commercial like this where the guy just kept on typing the wrong number for some reason, and he was getting charged for it, And then Saturday Night Live did a skit on it, and they were like, we don't care how dumb you are, we'll still take your money. So anyway, there's an exception because I hit return. But here's the point: is that you enter this number and you're trying to get the user to enter this value. And so if I run this and I actually do give the right value, then like 6 or something like that, then you reach done. So this is a case where you do want, in some sense, an infinite loop until the user gives you the value that you're asking for. And I forget if I did this example in the course or not, but I probably did, because I want people to know how to use these from a practical standpoint when it comes to controlling user input or controlling the conditions within a program, so that you don't leave that loop until that condition is actually satisfied. So that's all I have to say today for ifs, fors, and whiles. I'll take any questions to bring something to a close.
Well, I'll give everyone a chance to answer some stuff. I could not, that was too quick. I couldn't find the SNL skit you were looking for. So I don't know the timing for it. But I did have a question just personally for myself. So when you're programming, are you just using a regular like QWERTY keyboard with a numpad on the side, or what's your setup when you're doing this stuff?
Oh, I'm just using, right now I've got my laptop, so I'm just doing a QWERTY with numbers on the side, basically.
Oh, so you do, but you have the numbers on the side. You don't have like that top bar that they kind of do.
And I have the top. I have numbers on top, and I have numbers on the side as well.
Oh, okay.
Mm-hmm.
All right. Just padding for time to see if people have questions. Where do you type? Do you tend to like go up top, or do you tend to like go down to the right?
I tend to go up top. Usually I go up top.
All right. Well, we padded just enough time. We have a question. How would you write a do while statement?
Again, so it all depends with the while statement. It depends on where you're creating the conditions, right? So either when the test occurs, you have to, it all boils down to when the test is occurring. When you get back to the top of the loop, there's going to be a condition that gets tested. So as I was saying before, with something like this, let's just go back to this example. I set I equal to 0, and then I say while, I is, less than 10, for instance, and then I say I plus equals 1, and then maybe I'll print, I print I like so, okay? Then in this case, I'm putting the print statement afterwards. And let me come back over here.
Seems like an infinite loop we've been
I
talking.
know, I got my infinite loop here. While I is less than 10, I forgot that. There we go. While I equals 1. There's a typo right there. Okay, so
Pretty easy.
It's easy to run an infinite loop. Okay, plus equals 1. So in this case, you're adding 1 to I, and then you're printing the value out. And so the condition is that P, name P is not defined. I don't know what's going on there. So I could also put the print statement in front as well. So if I put the print in front, then what I'm doing is I'm adding 1 and I'm printing out beforehand. And so what's this exception? What am I doing here? It says, I gotta move the thing over here. P is not defined. I don't know. There's no P here, so maybe I'll do this and see. Huh. That's down here.
You got a P down at 10.
I had my screen thing, my Zoom screen thing over the. Okay. All right. And so the anything where you're saying like do unto or a while do or whatever, it just depends on where you put the condition with respect to where the test is taking place. And so you have to kind of like rearrange your code to be aware of the fact that the condition is being tested at the beginning of the loop. So that's how you deal with all the other set of whiles that you could generate within other computing languages.
All right. That's excellent. I think we're at time here. I'll wait for some stuff to catch up just to make sure, but I think that the questions in the chat are now being answered. People were like, I think you're on line 13. And then you do like my Zoom chats on it. But everyone, thank you so much for joining us. Again, this is for Sailor.org's Introduction to Python course that you can find on Sailor.org or CS 105. If you'd like to continue the conversation, you can always put something down in the comments. If you have a question that can't be answered by the community, we'll bring it up next week in the video. Of course, you can also go to the discourse forums that will help you with that. I'm sure I'm forgetting something. Replit, the program being used, is in the description below, as is the other videos in this course. If for some reason you watched all of Unit 3 and hadn't done Unit 1 or 2, we have recaps of those. And I'd just like to thank Dr. Eric Sakk again, and I'd like to thank everyone again for joining us. And I'm just gonna vamp for a second.